Hi everyone, my name is Lydia and this is what I wish they taught me about econometrics and introduction. In the previous videos, we've talked about the mechanical properties of OLS, how they've always true, and we also showed the math. Now it's time to finally introduce the statistical properties of OLS, which will hold true only if certain assumptions are satisfied. There are many statistical properties, and I have laid them all down here for you, at least the first four ones, that will bring us to saying that OLS is the blue estimator with the lowest variance, meaning the best linear unbiased estimator with the lowest variance. However, we're going to start only with the first property today, which is the OLS estimators are unbiased estimators of beta null and beta 1. You'll see here we are now finally talking and using the expectation operator, which we explained in the previous video. Before I dive into the assumptions that kickstart the properties, I would like you to also notice something very carefully. In here, we're working with beta null and beta 1. And we have that the expectation of beta null and the expectation of beta 1 hat need to be equal to these beta null and beta 1 that don't have the hat. Keep in mind, these beta null and beta 1 in here, they are the values of the population. So these are the true values of the population. However, keep in mind, we never have the tools to get information on the entire population. That's why we always work with samples. And the properties are the ones that tell us how does OLS behave across all the repeated samples of the world. And that's why we are making use of the expectations in here. And what we're saying with the first property is that, well, across all of these repeated samples, sometimes I'm going to get something that it's less, sometimes something that it's more than the actual value, the true value of the population, but on average, I'm going to hit the true value of the population. So again, reminder, beta null here is what's coming from your sample estimation, and beta null without the hat, it is what you expect to be like the population value for that. I am not going to continue on the other statistical properties. They are written in here, but we will stop on them in next videos, and we will look at both the intuition and the math of what each and every one of the statistical properties is telling us. However, without further ado, let's start on the first few assumptions. There is a little bit of a disclaimer that I am going to start with, and that is, depending on the book that you are using and depending on the type of data, plus the type of regression, different books are going to use different labels for the assumptions that need to be fulfilled for the statistical properties. What I mean with the type of data, meaning do I have cross-sectional data, or do I have time series, or do I have panel data? Type of regression, do I have a simple regression, or do I have a multiple regression? Keep in mind, simple regression is just y equals to beta null plus beta 1 x1 plus error term, meaning you only have one x, and multiple regression, y equals to beta null plus beta 1 x1 plus beta 2 x2, and you can add as many betas as, like, an x variables as you need. Now, continuing on the disclaimer, you will see for the simple regression labels such as SLR, while for the multiple regression, you'll see labels such as MLR. The other time that labels might be changing is when we deal with time series, and we're going to see TS for the assumptions. Keep in mind, most of the times the intuition behind these assumptions is the same. However, the wording needs to be adjusted depending on whether we're working with SLR, MLR, or time series. Let's start with the first assumption that is needed. The first assumption is called the linearity assumption. And what that tells us is that the population relation is linear. If I have a simple regression, for instance, it would look beta null, beta 1, x1 plus an error term. And someone might open their data and see, let's say, data that looks like this. Very clearly here, the relationship looks a bit different. We are very conscious of the fact that until this particular x in here, the values are increasing on y, but once we pass this x threshold value, then the values start decreasing. So obviously, the relationship in this data doesn't seem very linear. It does look quadratic, but keep in mind, the linearity assumption that we are talking about here, it's not about the shape of the relationship. It literally means how is instead the beta entering this equation, and it should be in a linear shape. So beta 1 here is correct. If I had instead, let's say, a beta 2 squared x1, then this is what is wrong. Okay, so beta 2 cannot be quadratic. It can only be linear. And if your question is like, but Lydia, it's very clearly from this graph that it's this relationship shape is not quadratic. So how will the OLS fix for that? There are many different ways to fix for that. And the most used version of it is that instead of having, on top of having just the x1, we can also have, let's say here, beta 3 x1 squared. Okay, so in this case, the beta 3 is still linear, but the x1 squared, it's squared, okay? So on top of x1, you have x1 squared. And again, the linearity is not about the relationship of your y and x, but it's how the beta is entering this equation. And in here, the beta 3 also is linear, so we have sort of satisfied this linearity assumption. This assumption will apply to both the simple regression and to the multiple regression. That's why you will see it in different books mentioned in both SLR and MLR. The second assumption, I am actually going to skip, and there is a reason why I'm going to jump directly to assumption 3. But I will talk about the second assumption in a separate video. Assumption 3 tells us that the variation in x should be greater than 0, meaning there needs to be variation in your x variable. Which, for most of you, this will make very intuitively a lot of sense, because what is the point of you running a regression to find the relation between y and x if your values in x are not changing and your values in y are changing? How exactly are you going to look for patterns in there if your x variable is not changing much? Now, this assumption, you will only see it under the assumptions needed for a simple regression. The equivalent of this assumption for multiple regression cases is instead going to sound as either, this is for those working in matrix form, that the columns of x must not be perfectly correlated, okay? Or the scalar version of it, so for whoever works with scalar, is that there's no perfect collinearity. Okay? For those of you working with the matrix versions, this the columns of X must not be perfectly correlated is equivalent to saying that our X prime X matrix is invertible. Okay. Now, why are these two assumptions so important that I actually had to jump the second one? It is because based on assumption 1 and assumption 3, we have what we call the most basic conditions for the existence of OLS. What does it mean? Does it mean that it's okay to go ahead with OLS and continue just as long as we have these two assumptions? No. The answer is no. It is that, well, now I have enough conditions for me to be able to run the maths behind OLS. However, if that maths is reliable, that is still to be seen because we still need to add further assumptions. I hope this was helpful to kickstart you on the assumptions. So keep in mind, we've seen assumption 1 and 3 that create the basic conditions for the existence of the OLS. However, for us to be able to rely on our OLS assumptions so that we can say, okay, statistical property 1 checked, we need 3 more assumptions, which we will see in the next video. See you soon.